Sequences. A recursive sequence is a sequence where you're given a sub 1 and the value of a sub n plus 1. And that's how you determine the following values of a sub 1, a sub 2, up through a sub n. So here's an example. If we define the recursive sequence by a sub 1 equals 1 and a sub n plus 1 is equal to a sub n plus 1, then here's what we get. We get a sub 1 is 1, a sub 2 is a sub 1 plus 1, so that's 1 plus 1, which is 2. A sub 3 is a sub 2 plus 1, which gives us 3. A sub n, it looks like, if we follow the pattern, is going to be equal to n. Let's check that we're right. If we're correct, then a sub n plus 1 will be equal to a sub n plus 1, which is n plus 1. Okay, and that follows the pattern. So if we want to write out our sequence, our a sub n, it's really easy to write it as just the sequence n. Here's another example of a recursive sequence. Let's define it by a sub 1 is equal to 1 and a sub n plus 1 is equal to a sub n, the previous term, times n plus 1. Then here's what we have. We start with a sub 1 is 1. A sub 2 is going to be 1 times 2. A sub 3 is going to be a sub n, which is 1 times 2 times 3. And if we continue on in that pattern, you'll see that our a sub n is going to be equal to this. We can double check that we're right by looking at a sub n plus 1. The formula says that's going to be equal to a sub n times n plus 1. A sub n we said was 1 times 2 times 3 up to n minus 1 times n, and then times 1, n plus 1. So it looks like we have the right formula. Now this should bring something to mind. It should bring into mind factorials. Remember that n factorial is the product of all the numbers 1 through n, or you could write it backwards as the product of n down to 1. So using this n factorial notation, we get that a sub 1 is 1 factorial. A sub 2 is 2 factorial. A sub 3 is 1 times 2 times 3, that's 3 factorial, and so forth and so on. So we can write this sequence as the sequence n factorial. Sometimes the critical information about sequence is whether it converges or not, with the limit being not important to us at all. So what we're going to look at now is a way that will help us decide if a sequence converges or diverges without having to find the limit. So we'll start with the definition. We'll say that a sequence a sub n is called increasing if each successive term is strictly greater than the one before. We will call it non-decreasing if each successive term is greater than or equal to the term before. So it's never going down, it's not decreasing anywhere. And similarly, we'll define decreasing to be if each successive term is smaller, or non-increasing if it doesn't increase. That means each successive term is less than or equal to the one before it. If a sequence is either non-decreasing or non-increasing, which includes all 4 of these cases, then we say it's a monotone sequence. If the sequence is increasing or decreasing, so there's no equal sign here, then we say it's strictly monotone. So here's a nice little theorem. It says that if we have a non-decreasing sequence, there are 2 possibilities. Either there's a constant m such that a sub n is less than or equal to m for all n, in which case the sequence converges to a limit L where L is less than or equal to m. The smallest such m that you can find is called the least upper bound. So it's the least upper bound on that sequence. My sequence is never going to go above that. Otherwise, if this isn't true, then no such constant exists, and in that case that means the limit of my sequence is infinity and it diverges. Now there's a matching part to this theorem for non-increasing sequences. Just like you would expect, if you have a non-increasing sequence, there's two possibilities. Either there is a constant m such that a sub n is greater than or equal to m for all n, and when that happens, the sequence converges to a limit L, and that L has to be greater than or equal to m. And the largest m that we can find is called the greatest lower bound. If a greatest lower bound doesn't exist, then the limit of our sequence is negative infinity and it diverges. So a nice little way to summarize that theorem is that if you have a sequence that is monotonic and bounded, either above or below, then it converges. So let's show that this sequence, 5 to the n over n factorial, converges. So since a sub n is greater than equal, since a sub n is greater than 0 for all n, we know that if a sub n is less than or equal to a sub n plus 1, that'll be true if and only if 1 is less than or equal to a sub n divided by a sub n. And vice versa, if a sub n is greater than or equal to a sub n plus 1, then the ratio 1 greater than or equal to a sub n plus 1 over a sub n must hold. So we're going to use this idea to help us decide if our sequence converges or diverges. So the terms of our sequence a sub n were 5 to the n over n factorial. That means our n plus first term is, everywhere there's an n here, I plug in an n plus 1. So it becomes 5 to the n plus 1 over n plus 1 factorial. And when you write this, you have to put parentheses around the n plus 1. If you just wrote n plus 1 factorial without the parentheses, you're saying you're adding the number n to the number 1 factorial. So it's really important that you put parentheses there. All right. Now if we look at the ratio of a sub n plus 1 over a sub n, then we put in those two terms. We simplify this fraction by flipping the bottom term. Now we take this right here, and I'm going to rewrite the 5 to the n plus 1 as 5 to the n times 5, and I'm going to rewrite n plus 1 factorial as n factorial times n plus 1. Now when I do that, you can see that the n factorials will cancel out and the 5 to the n's cancel out. So I get that my ratio is equal to 5 over n plus 1. Now when n is equal to 1, 2, or 3, then hopefully you can see that this ratio is going to be greater than 1. But if I look at n greater than or equal to 4, then that ratio is always going to be less than or equal to 1. So going back to what we said at the beginning of our proof, if we just ignore the first three terms of the sequence, then we know that our sequence is now decreasing, because what did we say? We said that the ratio is less than 1. So since our sequence is decreasing, and since all the terms are positive, we know that our sequence is bounded below by 0. Our theorem tells us that this sequence converges.